Okay, welcome to this tutorial about the concept of phasor and its application for analyzing AC circuits. So if you have not watched our previous video, which was an introduction to complex number and how we can convert complex number to phasor, please stop here and go watch that video first and then come back to watch this one. Okay, let's get started. So, what are the motivation here? Why even we bother to talk about the new concept of phasor? Because we can essentially define or derive the equation for AC circuits in time domain. The answer is yes, we can drive this equation, but as you have seen before, these are differential equation where oftentimes it's complex to obtain the solution. So essentially using this concept of phasor and transforming this sinusoidal function into a simple complex number will simplify the analysis of AC circuits, and it is like we avoid solving differential equation if we are using phasor, and we only need to handle and manipulate algebraic equation, so it literally simplify everything. Okay, so now let's talk a little bit about the concept of phasor. And what you can see here, we have this time domain function v of v equals to v of m, which is the magnitude cosine of omega t plus phi, where omega t obviously is the time dependent component and phi is just a constant phase angle, and it's not a function of time. Okay, it is not. And we want to convert this time domain function to a phasor. So first of all, this time domain function can be defined as a real part of v tilde time e to the power of j omega t. But what is the v tilde? V tilde, we define it here. And essentially what you see here as v tilde is the phasor, where it is equals to v, which is magnitude here, v of m, and e to the power of j phi, where phi is just the angle. So essentially, the phasor just take the magnitude of your time domain function and its phase angle, phi, as you can see here. And I can write this v of m to be consistent with this v of m here. Okay. And essentially, this phasor in the complex format, we can also write it down as just v of m and the angle of phi, where essentially this is the phasor. Okay, this is the phasor. This is the exponential complex format, and this is the rectangular format of the phasor, because these are all like you can convert to each other, as we actually discussed about this topic in the previous video on complex numbers. Okay, so we now know how we get the phasor, which is the phasor here. If you have the time domain function, okay, this is gonna be your phasor. And moving forward, I would like to talk about this phasor, and we will show that how using this concept, it will simplify the analysis of AC circuit. And essentially, you would see that any derivative will simplify to a multiplication, and the integral will simplify just to a division. Okay. Uh, mm, So sinusoidal signals generally defined as has a magnitude. Obviously, they have their angular velocity, and omega t we also call it the argument. Phi is the phase angle. These are like the main component of these sinusoidal signals. Now, as we mentioned before, the essence of phasor is based on the application of the Euler formula. Whereas you can see here, this complex exponential relate to its Cartesian component of it. And this is the the basis of phasor representation. Okay, a definition of the phasors. If we have a time domain function as a cosine function. And by the way, the phasor definition for AC circuit analysis is based on the cosine function. Okay, so this cosine function defines the voltage where the magnitude of this voltage is V of M, and then it's the time domain function is a cosine of omega t plus phi, and omega t is the actual time dependent part of it, but phi, the phase angle, is a constant, it's not a function of time. And when we want to convert these to a phasor, we essentially only use the phi, and we'll drop the dependent time function as we mentioned before. Okay, the concept of phasor, as we mentioned before, has the magnitude and angle, and you can represent it in the rectangular format if needed. However, typically we just use the polar format, and that's very useful if you want to take like any differentiation or integration or multiplication and division. But we can convert between rectangular or polar as needed. Okay, differentiation and integration. So if you have this time domain function for the voltage, electrical voltage, and if you want to take its derivative, that will reduce to j omega times v tilde, which is essentially the phasor. And if we have time domain function for the voltage as v of m times cosine of omega t plus phi, we want to take this integral, and if you want to show this integral in the phasor format, it will just reduce to a division, where essentially you divide your phasor by j omega. Okay, so you can see that how it simplifies and convert the calculus just to algebraic equation. In the next slide, we would like to have like a very brief proof of these two equation here, and I think it's going to be insightful for you guys. Okay, let us define the cosine function for our analysis, as we mentioned before. The topic of phasor for circuit analysis is based on the cosine function. So we have this time domain function for the voltage v of t equals to magnitude v of n times cosine of omega t plus phi. Okay, now let us use the Euler formula to convert this into a complex number. Okay, let me actually add v of m here. Okay, now v of m cosine of omega t plus phi is actually the real part of v of m times e to the power of j omega t plus phi. Now, these I can break it into two exponential. One is e to the power of j omega t, and the other one is e to the power of j phi. And I would like to actually write it down here, okay? And the reason I'm writing it down so you guys can see how this happens. I type real part of V of M e to the power of, okay, J E times e to the power of J omega T, okay? And now what happened here is that if I just take this part, which essentially this part is, it doesn't have any time component. I can call this part V tilde or the phasor. And essentially it is just the magnitude of V of M and the angle of B. Okay, perfect. And that's essentially what you can see here as the V tilde, okay? Now, we actually define it V tilde here. And now let's now that we know that the time domain function can be write down as the real part of this complex number. Now let's go ahead and take the derivative of this complex number. Okay, derivative of this time function is derivative of real part of phasor times e to the power of j omega t. Remember, phasor doesn't have any time component, so you don't need to take a derivative of that. That's just a constant or a coefficient. But we're going to take the derivative of j omega t, and derivative of exponential are like straightforward. It would be just the coefficient of exponential, j omega t, times the exponential, e to the power of j omega t, times the phasor. Now, reorganizing this, we arrive at this equation, j omega times phasor times e to the power of j omega t, and we can say this in the phasor domain, which is the frequency domain, derivative of time domain function reduced to j omega times the phasor, okay? So j omega times the phasor. Now, similarly, if we want to take the integral, again, integral of v of t d of t is integral of real part of phasor times this exponential. And again, phasor is not a function of time, so it comes out of the integration. You can write it down here. And integral of this exponential is straightforward. It's going to be 1 over j omega e to the power of j omega t. And once again, if we want to convert this into phasor domain, this integration is just the phasor multiplied by or divided by j omega. So we actually proved that any differentiation would reduce to j omega times v, and integration would reduce to just phasor divided by j omega. Now, based on what we just showed here, the phasor in circuit analysis can simplify, I mean, for the resistor, because there is no like integration or derivative, it's a straightforward, like the relation between the voltage and current is going to be the same as time domain as current times resistance IR. For the inductor, okay, it's going to be j omega L times I, where this part actually, we're going to name it as the impedance. And if you have a capacitor, the relation between voltage and current will reduce to current divided by j omega c. And we can use the parameter z to refer to this j omega L or 1 over j omega c, and you just call it the impedance. This is just another way to represent the same concept. Essentially, these are all the time domain equation, okay? And as you can see, we have it also in the frequency domain and using the concept of phasors. So the first one is the same for time domain and frequency domain. But this second one, which is about the inductor, inductor in the time domain, voltage equals to the inductance times the derivative of the current. Okay, but hey, if you're using the concept of phasor, the derivative would just simplify to L omega J, and that's what you see here. So the voltage equals to L omega J times I, and these can be Z of L for impedance for the inductor. And similarly, if we take a look at the capacitor, the relation between voltage and current is an integration, 1 over C integral of I div t. Now, thankfully, if we use the concept of phasor, integral will reduce to 1 over j omega c times I. And we can also rewrite this as V equal to, if I multiply by j and divided by j, times 1 over j omega c, it will reduce to, so this would be minus 1. So it would be minus j times 1 over omega c. Now this format is also handy, when we want to use this concept for circuit analysis. Okay, so this is the impedance for our capacitor. And I guess let's take a look at an example together. Okay, what we have here is RLC circuit. We would like to use the concept of phasor, and we would like to solve this equation, meaning that we would like to find, if we have the equation for the voltage, we are looking to find the equation for the current. What is the current equation in this circuit? If we know the equation for the voltage, this is given, what's the current? And we would like to use the concept of phasor here to simplify our equation. Okay. So I guess the first thing that we do is that we define our voltage source as a V of M cosine of omega t, and the value of resistors is R, inductor is L, and capacitor is just C. And next thing that we would like to do is that we would like to define impedances. So for the resistor, it's just R. For the inductor, it's going to be J omega L, where omega is this frequency here, okay? And for the case of inductor is 1 over J omega C. And as we mentioned before, we can rewrite this as minus J times 1 over omega C. Okay, so once we have everything in the impedances, we can just look at this system as everything is just a simple resistors, and we can add them together to find the total impedances. In this case, all these three elements are in series as they receive the same current. So adding them together, we have this equation where it can simplify to R plus J times omega L coming from here, minus 1 over omega C coming from here. And this is our impedances. Now, we would like to, in the next step, calculate the phasor for the voltage and current. Now, the voltage was this simple cosine function. And as you can see in this cosine function, there is no phi. Essentially, phi is 0. Okay, it has only the time dependent component, and phase angle is 0. So the phasor is simply the magnitude V of m and the angle, which is 0. And the current can be obtained using the Ohm law as voltage in the phasor format divided by impedance. But our impedance is this function right here. Okay, so the impedance, the total impedance Z, if you want to do this division, we need to convert that into also a magnitude and angle. Okay, this complex number is defined right now in the rectangular format. We want to convert that into polar or phasor format, which is this type of format, the magnitude and the angle. Now, the angle, if we call it just theta, based on this part here, it would be minus theta because the angle of the numerator is 0. So 0 minus theta would be minus theta divided by magnitude of Z. And if we want to convert these now, because this is here is in the phasor format, we want to convert it to the time domain function. The time domain function also going to be a cosine function, and it's going to have the same frequency as the uh, voltage, input voltage omega t. But the phase angle here, it's going to be minus theta. So we're going to put minus theta here. And this is going to be your time domain function. Now, if you want to actually calculate this magnitude of z and theta, that's straightforward. And you can obtain it based on this total impedance function that we have here. So based on the total impedance function that we have here, the magnitude of z is the real part square, okay, r square plus omega L minus 1 over omega C square and a square root of everything, a square root of everything, which is going to give us the magnitude of Z. And the angle also is straightforward. It's going to be inverse tangent of the imaginary part, omega L minus 1 over omega C divided by R. I'm going to just draw like this simple thing here, just for clarification for the Z. Let us say this is Z. Okay, if this is Z, let us say that the real part, the value is just R, and the imaginary part, the value is omega L minus 1 over omega C. So now you can see that when we say like the magnitude of Z or this angle, theta, how we calculate it, okay? And that's going to be the magnitude of Z. This part is magnitude of Z. And obviously this part is theta. Okay, now let us just solve the same example, but with some parameter values. So you can also practice it at home and to see if you can find the same answer. Now, in the same RLC circuit, the value for the R is 10 ohm. The inductance is 0.1 Henry, and the value for the capacitance is 100 microfarad. The input voltage has the magnitude of 50 volt times cosine of 1000 T. So omega is 1000. And from there, we want to calculate uh, the value for the inductance and also capacitance. And in the phasor format, it would be omega L. And the phasor part of that, or I should rather say the impedance part of that, it would be this times just J Okay. If we are talking impedances, this would be times J. And if we talk impedances here, this needs to be multiplied by, sorry, divided by J. So this divided by J. And in the next slide, we add the all the impedances together. From the resistor, it's just R. And for the inductor or capacitor, it would be J times X of L minus X of C. And that's going to be 100 minus 10. And it would be 10 plus 90J. So here the magnitude is, the magnitude of these impedance would be just 90.55, and the phase angle would be 83 degrees. So if we take a look at the voltage function, the phasor would be 50 with the angle of 0. And from there, we can calculate the current phasor to be 50 and angle of 0 divided by our impedances, which is 90.55 and angle of 83.66. That will reduce to 0.55 and angle of minus 83. And then from there, we can write down the time domain function as 0.552 cosine of 1000 t minus the phase angle of 83.66, where again, the same frequency that we had it for the voltage, we should have it for the current as well. Okay, let us have like a few examples to solve it together. So about this practice problem, I would like you guys to pause the video and think about it and try to solve it, and then watch the rest of video for the solution. So the first problem is we would like to convert time domain voltage, which has a magnitude of 10 and the frequency, angular frequency of 1000 t, and the phase angle of 30 degree to a phasor format. Okay, so the phasor format literally has two components. The first component is just the magnitude, which come from here, just 10. And the second component is the angle. But here, there is something that you guys got to pay attention. The concept of phasor was developed based on cosine function, okay? But here we have a sine, okay? We have a sinus function. So the first thing is that before I'm looking for the phase angle, which is here 30, before I just pick 30, I need to convert the sine function into a cosine function. And as you guys know, sine of omega t is equals to cosine of omega t minus 90 degree. Okay. Now adding that, 30 minus 90 will reduce to minus 60. And now I can pick this as the phase angle phi, which can sit here, okay? If someone go ahead and just put 30 over there, obviously it's wrong. You should not do that. You should not do that. Should first convert it to cosine and then see what is the phase angle. And once again, that is because as we developed the phasor concept, we developed it based on cosine function, okay? So let's be consistent there. Okay, this is the second problem. Once again, I would like you guys to pause the video here, try to solve it, and then look at the solution. Essentially, we have an RL circuit, okay? So there is a resistor and there is an inductor, and then I have this AC voltage source of 20 cosine of 100t, okay? So this is R, and obviously this is L. So I'm looking for the time domain function for the current. So the way I solve it, I'm going to use the concept of phasor. and I'm going to use find out what's the value for impedance for R and L. And then once I convert that, I'll go from there and I find out the phasor for the I as the phasor for the voltage divided by the total impedance. Okay, the total impedance gonna be the impedance of R plus the impedance of L. Okay, and that's it. So let's take a look at the solution. So first thing first, the angular frequency is 100 radian per second. So from there, we can go ahead and find out the value for the inductive reactance, where essentially it is omega L. Okay. Now from here, the impedance for the inductance is Z of, I show it with Z of L. That's going to be just J times X of L, or you can just write it down as J omega L. And that's what we have it here, okay? And the total impedance is just R plus J X of L. And obviously R and L are in series, so we just add them together. And from there, that's going to be 10 plus J times 10. And this is the rectangular format. We convert it to magnitude and the value and the angle, which is the phasor, okay? This is the phasor format for the impedance. And the reason why we converted to the phasor format, it simplifies the division. Now, as for the voltage, it was just a cosine wave. So the magnitude was 20 and the angle was 0. And as for the impedance, the magnitude is 10 square root of 2 and the angle is 45. Now that will reduce to square root of 2 and the angle of minus 45. And from there, the time domain function would have the magnitude of square root of 2. Obviously, the frequency stay the same. Again, angular frequency going to be 100 radian per second. And the phase angle for your current would be minus 45. Okay. The last example is just very straightforward. We just want to use some diagram because these phasors are like vectors. And the first one is just the magnitude of 10 and angle of 0, which is this is the first one. The second one is like the same magnitude of 10, but obviously the angle is 120. And finally, the last one is 10 and minus 120. And this is a balanced three-phase AC voltage, okay? Thank you so much for your attention. I'm going to upload another presentation where essentially we're going to use this concept of phasors and impedances to analyze electrical circuit based on nodal analysis as well as mesh analysis. So please watch that video as well. Thank you so much.